The second gas law that we'll be looking at is the relationship between the volume and temperature gas measurements. So we start with our combined gas law again, which is P1 times V1 over T1 times N1 equals P2 times V2 divided by T2 times N2. Now, if pressure and moles are constant, the new law, if you look at it, you would get rid of this and this, so you'd get rid of the pressures, and if the moles are constant, you could cancel out the moles. So what you'd be left with is this, volume over temperature. So V1 over T1 equals V2 over T2. This does present a couple of issues. One, the temperature must be in Kelvin. And the reason for this, Kelvin is a 0 and then moving forward scale. It's only positive, aside from, of course, absolute 0. There's no negative temperatures. And you can see if you were to have a negative temperature in one of these, the math, if you were solving for volume, you could end up with a negative volume. Now, you can't have a negative volume here on Earth. Something cannot take up a negative amount of space. So you need temperatures to be positive so that you have a positive volume. So if you're ever given temperature in Celsius, which you will, you need to convert it to Kelvin using this conversion, Celsius plus 273. This is known as Charles' law. The other issue that shows up, I find, is solving for temperatures when they're in the denominator. So one of the simplest things that you can do to save yourself some time is cross-multiply this formula so that you get rid of the denominator. Just because solving for T1 or T2 sometimes presents some difficulties with algebra. And what we're going to look at now is a real brief animation to demonstrate this law. And so again, looking at this animation by Cairo Publishing Company, you can find it at preparatorychemistry.com. This is going to be a demonstration of Charles' law. And what you have with Charles' law is you have constant volume and constant that's not right at all. Constant pressure and constant moles. Volume and temperature will be what is fixed. So the pressure is able to be regulated or adjusted, and then also the number of moles is constant. So there's going to be no leaks in this container. And so when I start the animation, what's going to happen is the temperature is going to increase. And so you'll see this red thermometer start to increase. Now watch what happens when the temperature increases. As the temperature increases, you can see the particles in here are moving faster. Faster particles moving around faster particles moving is going to cause them to push more strongly against this piston, which is now movable because volume is no longer fixed, and so it will push up. So I'm going to go back so we can watch that again. So you can see the temperature, the speed of the particles isn't too great. Then as we turn it on, they move faster and faster and faster and faster and push up against it, and so then the volume increases. So a higher volume leads to a higher temperature. The opposite would also be true. A lower temperature would equal a lower volume. So once again, this is known as Charles' law, and it is the relationship between volume and temperature. And of course, we're going to have some math associated with this because we can take measurements, and so we'll do a couple of sample problems associated with this. First example. Again, word problems, you really got to read carefully for the units that you see. You also got to read for the context of what's the initial and what's the final conditions. So you've got a sample gas. It has a volume of 5.5 liters and 25 degrees Celsius. So that's the initial conditions. It's now asking what will the volume be. So that's looking into the future. That's your second conditions if the temperature is increased to 100 degrees Celsius. So there's our holding tank setup where we're going to write out what all of our variables are. And here they are. You got the setup there. Now, one thing to pay attention to, these are units of Celsius in temperature, so you have to convert them to Kelvin. So we'll go through each of those two conversions, adding 273 to each. Your two new temperatures now are 298K and 373K. Setting up the algebra, you got V1 over T1. Here's your rearrangement, solving for, doing a little cross multiplying, solving for V2, because that's what we're looking for. Those are your variables set up to go. Plugging in your numbers, you've got T2 here, 373K times V1 divided by T1. That's going to equal V2. And then you should get 6.88 liters as your answer. The second sample, it's going to be the same setup. My recommendation is that you take care of this, try it on your own first. So you might want to pause the video and then I'll be going through an explanation. And so reading through the problem, here we go. Your initial volume is 375 milliliters at STP. Now STP, you may remember, is standard temperature and pressure. So we'll be filling that in based on what standard temperature and pressure mean. What temperature must the gas be heated to? So what temperature? It's going to ask you for, in the future, T2. So that's our unknown. And to occupy 500 milliliters. So we're increasing the volume, 375 to 500. So that means that the temperature must also increase. So here's your setup. Standard temperature is 0 degrees Celsius. Of course, you have to convert that to Kelvin. So that's going to be 273K. From there, here's your initial setup. Cross multiply to get rid of the denominator, because again, we're going to be solving for T2. So we need to prepare for that by getting it in the numerator. You can't just divide by V2. That's going to give you the inverse answer. So again, solving for T2 now, to get it by itself, you get this setup. Now you can plug in your numbers. T1 times V2 divided by V1. And your answer is this, in Kelvin. If you were asked to find the final temperature in degrees Celsius, that doesn't mean you can do your calculation in Celsius. You do the full calculation in Kelvin just like we did, and now at the end, what you would do is subtract 273 to get to Celsius. This one didn't ask for that necessarily, but if it did, that's what you would do. Now we're going to be looking at the relationship between pressure and temperature. So with pressure and temperature, the other two are going to be held constant. So here's our combined gas law, canceling out the constant volume and constant moles. It's going to look pretty similar. The algebra is going to be pretty similar to our previous Charles law, but this is a new one because it's based on pressure and temperature. Is this a direct or an indirect relationship? To answer that question, what you got to look at is how do they change, the two variables. Does a change in one correspond to the same change in another? Meaning, if I increase the pressure, do I increase the temperature? Thinking back to the volume temperature law, an increase in temperature pushed that piston up, which is going to increase the volume. So higher volume leads to higher temperature, or vice versa. Lower temperature leads to lower volume. Since this mathematically sets up the same way, you're dealing with a direct relationship. If you increase the temperature, you're going to be increasing the pressure on the other side. So they're going to vary together. That's a direct relationship. And here's the reasoning. The higher temperature implies higher particle velocity. Because the particles are moving faster, they're going to hit the walls with more force. If they're hitting the walls with more force, that's going to be a higher observed pressure. So you have two ways of understanding this as a direct relationship. You can look at the math formula and evaluate the fraction, or from a chemistry concept standpoint, understanding how particle motion works. Looking at our first practice problem, here's your basic setup, just giving you the numbers. The holding tank is over there on the side. Just as with volume temperature, given units in degrees Celsius, you do have to convert those to Kelvin. So, plugging in our numbers here. Notice that here it's asking for what is it in Kelvin, because that's what the calculation is going to end up to be. First thing you got to do is convert your Celsius number to Kelvin, so plus 273. Set up your initial formula. Since we're solving for T2, T2's in the denominator. You need to cross multiply and then divide to solve for T2. Plugging in your numbers, you get this, making sure everything is set up right. Again, you can look at the wonderful beauty of units. Atmospheres cancels out atmospheres, leaving you with Kelvin. Kelvin is a unit of temperature. That tells you you did your algebra right. Always look at that. Sometimes you may run into some trouble there, and you'll know if you're doing the problem wrong based on how the units stack up. And so you should end up with a final answer of about 307 Kelvin. 306 and change, I think, is what your calculator should end up to be. Again, if you were asked for it in the final temperature in degrees Celsius, you would then need to subtract 273 to get there. But you cannot do a Celsius conversion with these gas laws. Here's another. The pressure given of the gas sample, 1.50 atmospheres. The temperature is 35 degrees Celsius. If the temperature is decreased to 20 degrees Celsius, what will the new pressure be? And so just to check and make sure you've got an understanding of the pressure, think about will the new pressure be larger or smaller? And then what's your explanation? And when I say there use KMT, I'm asking you to use kinetic molecular theory, so thinking about the motion of the particles. So think on that for just a moment. You might want to pause the video. And so, temperature's decreasing, down 15 degrees Celsius. Smaller temperature means slower particles. Slower particles means they're not going to be hitting the walls of the container as fast. Not hitting the walls of the container as fast leads to lower pressure. So the answer you should get is a lower pressure. So conceptually you should expect that. Now we just got to do the math. You're given 1.50 atmospheres as P1 in an initial 35 degrees Celsius. You're given 20 degrees as your new temperature. Your P2 is your unknown. Convert your Celsius temperatures to Kelvin. Always make sure to do that. Set up your numbers here, or set up your formula. Cross multiply. It's the easiest way to simplify everything. Finding P2, you should end up here. And then, of course, plugging in your numbers, you'll find that P2 has this setup, T2 times P1 divided by T1. Doing the math, pretty straightforward. Notice again, kelvins cancel. You've got atmospheres, which is a unit of pressure, so you're good to go. And you should get about 1.43 atmospheres. And so thinking that through, did we get a smaller pressure? Yeah. It wasn't a significantly smaller pressure, but then our temperature wasn't a big change either, going from 35 to 20 Celsius. And so to recap what we've done in this lesson, we learned that gas measurements can change, and if you change one, it'll often affect the others. Sometimes measurements can be held constant to where a change in one measurement will only affect, say, one other one, like pressure and volume might have one effect on another. For each of those individual gas laws that we looked at, and we looked at pressure volume, we looked at volume temperature, and pressure temperature, what you need to know is the concept behind it, meaning the explanation based on kinetic molecular theory, and then you also need to be able to perform the calculations, paying attention to units and, of course, algebra. And that's it for the gas laws relating to the combined gas law for this lecture.